Good day, all of you. Hope you are fine at your place. And now we are continuing our online lecture today. In the last lecture, we discussed about elastic settlements, particularly schematic settlement. Now we are going towards the consolidation settlement. And you know that in a consolidation settlement, we require the stress distribution or the stress due to the applied load at the surface or at a particular depth. Uh, Therefore, it is necessary to study that stress distribution, and once we complete the stress distribution, then we'll again come back to the consolidation setup. Okay, so topic of the today's online lecture is stress distribution. It's our second and third in the subject advanced formation engineering electric. Let's go through a basic difference between the vertical stress and applied stress. We already studied the soil mechanics that the stress increases because of the self-weight vertical direction, it is gamma into z. Whereas the stress due to the applied load, this applied load may be anything, point load, or it may be uniformly distributed load, for example due to the footing of different shape raft. Okay, you see here approximately disperse. As it disperses, the area increases, therefore load upon area, the stress goes on decreasing. It means the effect of this load on a particular level, maybe surface or at certain depth, it goes on decreasing, and it diminishes after certain distance. Approximately, we can see here. Later on, we discuss how the stress decreases. So this shows that vertical stress increases with the depth, and but the load on the top, if you apply stress, the stress decreases as the depth here increases, not decreases, because the depth is increases. Corrected this. Okay. Different theories are available to determine this decrease in the stress. That is called a delta sigma. Elastic theory is there, Boussinesq theory is there, Westergaard theory. Boussinesq theory is the most widely useful, particularly for the foundation to determine the settlement. Westergaard theory is useful for a plate element, maybe like a pavement or even some of the raft. Now, before we move here, we must go through how to designate the stresses in a particular point of a soil mass. Let us consider this is a surface and this is a small point, any point. It is represented by something like a cube, which is at a distance of x, distance of y, and distance of z. So coordinate of the center of mass of this element is x, y, z. Now how the stresses are designated? Okay. So first thing, the most important thing to designate the stresses is the plane. Let us see the ABCD is the one plane, which is a horizontal plane, and you can see the CB, the FG is a vertical plane. Now this plane is at a distance, if you see the perpendicular distance, this is also one plane. Okay, like x and y, the perpendicular distance between these two planes is a z. It is parallel to z direction. So therefore the stresses on this plane, the first letter is designated by the z. Now first is the stress perpendicular to area is the normal stress, and stresses parallel to the area are the shear stresses. All three stresses have a one common first letter Z that indicate this plane. Don't talk about the stress. First talk about the plane. The perpendicular distance of Z. Now this is very clear. First stress sigma Z. Now if I take a stress which is parallel to x direction, so this is a tau at a distance Z. That's why first letter is Z, and it's parallel to x. That's why tau xz. Now coming to the this one, the shear stress is again perpendicular distance Z and parallel to the y. Therefore, it is tau zy. Similarly, on this vertical plane, okay, this vertical plane, again this vertical plane is parallel to this plane, like a xz or zx plane. So these two planes are parallel and having a perpendicular distance of y. So therefore, all the stresses acting on this, okay, their first designation letter is a y. So first one is a perpendicular to this plane, vertical plane. That's why it is sigma y. Now shear stresses, if I take this shear stresses horizontal, either this direction or this direction, this is parallel to the x direction. Therefore, it is y distance away and parallel to the x direction. So it is tau yx. Similarly, a downward stress is again tau y, perpendicular distance y, and parallel to the z. So tau yz. Similarly, same element in a polar coordinates. Earlier was in linear coordinates. In a polar coordinates, what we consider the x, y, and radial r. So this radius r it will move, means this r will move in this direction. Let us consider one element again, similar element. It is again at a distance of z, the center of this mass is a distance x at a distance r away. At a distance r away. So one direction, the linear directions are x, y, z, and polar direction. If you see radial direction x, and one is a tangential direction, so which I shown here. A tangential direction is a t direction. So this is a tangential direction. This is the radial direction. So this element makes angle theta at this level, okay, and this width increases. Now here how the stresses are designated. Again, this plane, if you see the ABCD plane, is again parallel to the XY plane, vertical plane, and this is the vertical plane. This is at a distance of Z. This plane and this XY plane are at a distance of Z. So all the stresses here, okay, having a first letter of Z. Okay, now this is a perpendicular stress. That's why it is a sigma Z, and parallel to the plane are the shear stresses. Okay, here I purposefully left one stresses. How we'll write this? Now first tau, this plane. I always say that one must think about a plane is the x distance away, parallel distance between these two planes. So therefore, this is tau. It is distance z away, and it is parallel to the direction y. So tau z y. Another stress which is tangential stress. As I said that as this plane is a x distance, so first letter is a z and parallel to the r, just like here. First distance is a z and parallel to y. So this is tau zy. Similarly, on this surface, perpendicular to the radial is sigma r, just like a perpendicular to the horizontal area. This is a vertical plane. It's it is in the radial. But this plane, if you see, is somehow any tangential part. You can say it is perpendicular to this vertical plane, that is YZ or ZY. So this and this plane is having a distance of r. Therefore, all the stresses acting on this having first letter is r. This is perpendicular, and other two are the parallel. That's why you can see the tau r y, because the distance r parallel y. Here distance r vertical stress tau r, and this is parallel to the z, so therefore tau r z. So in this way it is designated like this. It can also be shown in a something like a line diagram. This is a top plane like this xy plane, and at a depth another plane, and I consider a point, same element having a point n, which is at a distance z, at a linear distance x, y, and here on the plane the radial distance r. Whereas between these two planes, if I draw a incline, something like a diagonal, so here this makes a perpendicular. So incline distance is r, vertical distance is z, horizontal distance radial direction is a small r. Therefore, capital R is equal to r square plus z square. Similarly, this r is again diagonal between the x and y. Therefore, it is r is equal to x square plus y square. So this point has a coordinate x, y, z. This figure is useful when we start about the first theory, that is the Boussinesq theory. It is also a very old theory, still very useful for finding the particular the stress distribution, that is sigma z. Actually, in a settlement we use a delta sigma z just to avoid the repetition of the delta. Here we are writing only the sigma z. Okay, and in this theory, if you see this earlier figure, we will concentrate first thing on the sigma z, and at the most one shear stress, that is tau rz. These two we will target. Now, what are the assumptions in this theory? Soil medium is elastic, homogeneous, and isotropic. All these words you know very well. Soil is a weightless. So most important is that in a vertical stress we use a gamma z, but here itself gamma is neglected, so therefore it is totally weightless. So self weight of that medium is not considered. Now soil is stressless or stress free. Before we apply a load, there should not be any earlier, or we can say initial stress acting on the medium. Stress distribution to the applied load is independent of type of material. It may be sand, it may be clay, sandy clay, or a matrix material like ammonium, anything. But the theory does not resembles on this type of material. Change in volume delta V is negligible. This is another important assumption, because you know when you applied a load, the settlement starts because of the load, whatever the load. We know in a footing, raft, okay. So delta V, settlement in vertical direction, radial direction are combined. That effect is neglected in this theory. Maybe one of the limitation, but still the theory is very very useful. Now considering this earlier figure, if you see here, along this radial distance the stress is sigma r, and this angle it makes with the vertical is beta. So I will not go much in more about the derivation. Only I'll just give a step earlier to this. That radial stress is resolved to cos beta vertical stress, and finally we get this important relations. You get 3 by 2. I just separated terms. 3 by 2. P is the external load, that is the point load P, which is applied at top you can see particular distance. Because of that, what is the stress develops sigma z and tau rz. We'll write 3 by 2, that point load p upon phi 1 upon depth z square, and this bracket you can see 1 upon 1 plus r by z, radial distance r on a plane, horizontal plane, and a depth z. R by z ratio is used, and this square, and entire power is 5 by 2. So you can see there is a nowhere the material properties or elastic parameters are involved in this equation. This is very simple. It just depends upon the external load and the the, the geometry. Similarly, in the figure which you have seen, the vertical, the tangential stress tau rz. If you see, this is almost similar, but this equation when it multiplied by r by z, you get the tangential stress also. Very simple correlation between the two. So if you see this equation earlier, if I take p and z outside, because p is applied load, that's why it is a variable, z also variable, other things you will find almost depends upon the ratio r by z. So if I separate this, that is p by z square, the remaining part I can write it as a influence factor called as kb, b because of the Boussinesq. So where kb is nothing but that remaining part 3 by 2 phi, I need a function of r by z. So if I put a ratio r by z, I get the influence factor and load upon z square, I get directly stress. So this depends upon the r by z. So a table is also given. Instead of calculating each time, a ready-made table is also given at an interval of 0.01. Okay, number of values are given. I just restricted as a sample up to say 6, around 6.15. So you can see this influence factor. Just to pick up this, put it here and multiply p by z square, you get this sigma z, similarly tau r z. Okay, now we'll move to how this vertical stress because of the point load. The theory is given for a point load, then it is extended for a different practical loads. So first, that vertical stress sigma z, how it distribute or varies on a constant plane at a depth z. So on any horizontal plane, how this sigma z vertical distribution varies. Okay, so here z is a constant and r is a variable. So in the expression, you can see the expression. This is the basic expression just now we have written in a short form in terms of influence factor. And now keeping the distance z constant, or which is known, given, we'll find out the sigma z for a variable distance of r. If I vary the distance, we get the sigma z. One thing we must keep in mind, that sigma z is always obtained at a distance x, y, z vertical direction. So keeping z constant and r variable, for example, if I take r by z 0 here, so if I take r by z 0, so it is 1 upon 1 plus 0, it is like unidentified value. Similarly, its ratio r by z itself is a 0. Okay, because suppose I put r is equal to 0, so r by z is 0. Z is a, suppose a unity value, a constant value, let us say. So if I put this as a 0, then what I get kb. Okay, So this part is a 0. So 1 upon 1, the power, therefore entire term is 1. I get 3 upon 2, 5, which is 0.477. Next I put, suppose r by z is 0.5. So here r by z is zero point 0.5 square and the entire is 5 by 2. I get 0.2733. So if I compare these two values, it means I am going down. If you see r is equal to, suppose z, I take a suppose unity, r was 0 at ground level, r at 0.5. Okay. Then what I get it, I am going down. So this kb value decreases. As kb value decreases, you can see sigma z is directly proportional to kb. Sigma z also decreases. So how much it decreases? If I take it the proportion, 57% decrease. Means when r by z 0 is a maximum, then it at 0.5 it decreases by 57%. So remaining values are given in a table. First value we discuss. If I put r by z is 1, then this sigma z value decreases. Sigma z, not correctly, decreases by further 17.7%. Again I go down, this ratio is supposed to, then it decreases 1.8, so almost nickel. So exactly here r is the first part 0 0.512. Okay, we get on a constant. Here the plane is constant. As distance increases, radial distance increases, the percentage decreases. It is clear from the next figure. You can see here z, I put it constant. Exactly below this load, the stress is maximum, and as you go away radial distance, it is not, this diagram is just not like a parallel to x or y. It is r, it rotates in all direction in a plane. So the stress decreases. You can see after 2 almost negligible. So stress is maximum. In settlement also we consider the assumption is that this stress is uniform, but actually you can see stress is not uniform. This the delta sigma z, which is used in a consolidation settlement, you can see it's not the same. It is decreasing. If I change this z to a different z, first conclusion very clear here, which is written that as you move radial direction, sigma z decreases. Now if I change this z, I take a different constant depth z1, z2, z3, z4. What you'll find that kb value, which was earlier we got it in the table, this kb value, that will decrease if I increase the depth. This shows that this distribution is a maximum at the tops. This distribution decreases as the depth decreases. So this diagram can be plotted at a different depth. One more thing is that this diagram, when it is plotted for a load is equal to 1, if I take load is equal to 1, then this diagram is also called as influence diagram. What is the advantage? That for a unit load I got the same diagram, and then I can move the load anywhere. Directly load multiplied by this ordinate, I get a stress. So that is the advantage of a influence diagram. Now we'll move to the second part. There are 3 parts we are covering for a point load. First was horizontal distribution, and now we are going for a vertical stress distribution. On a vertical plane. What is the meaning here? Earlier the z was constant, now z is a variable, r is a constant. Okay. So in the same value of sigma z, how it distributed when r value is a fix and z is a variable. So again, the Boussinesq equations I written in a short form in terms of influence factor, whereas this influence factor function of r by z. Now here I am varying the depths. Z is 0, 0.2, 0.1, any small interval you can take or close interval you can take. Let us say Z is 0. Now Z is 0, R by 0 and the term here R by 0 plus 1, 1 upon this term is unidentified. That's why this theory is not directly applicable for a point just below the node, that is depth is 0. Just away from the load, I take 0.001, theory is applicable. So except this Z is 0. Now let us take an interval point. Any closed interval you can take. Substitute KB first in the equation KB, 0.2 square pi by 2, you get KB value. And then substitute in the sigma Z, this equation, sigma Z. Substitute that depth, 0.2 square, and the KB value, you get this value. So for other values, this any closed interval you can take it. Okay. So for point 2 which we discuss here, we got KB value and we got sigma Z value. Now let us take a depth I change to 0.5. Here let us assume that R is suppose a 1, it's fixed. So 1 by 0.5 become 2. Substitute in the equation of KB, we get 0.00854. Then substitute in the equation of sigma Z, you get a value of sigma Z. Compare these two, stress increases. Here 0025 to 034 times load. Similarly, I go for a 1, ratio 1, then substitute in KB and find the stress. Now again you'll find stress is increase, 0.0844. Now again I little go downward, 2, so 1 by 2 R by 2.5. Again substitute in KB value and find out the sigma Z value. Here again what happened? First it was increasing, now it decreases. So there is some value in between the 1 and 2 Z, that there is a maximum value. So we'll find out this after completing the remaining calculations. So for 2, you'll find again the stress here it decreases 844.0683, and for 4 0.0256 drastically decrease. So the first stress is increases, somewhere it is maximum and then decreases. So we'll find out the point where it is maximum, as we discussed earlier, that between Z is equal to 1 and Z is equal to 2, the sigma Z value is maximum. So this is the basic expression. Now I simplified in this term. I taken this Z in the numerator and compare with this Z square, it becomes Z cube plus R square, which is simple for the further analysis. Now by our simple concept of the maxima, the variable in this equation is a Z, because R is constant. Therefore, I differentiate this equation with respect to Z equal to 0. My aim is to find out what is the depth at which it is maximum. I'll find out what is that Z. So it is a differentiation of a upon b. This term is a and b. So very simple differentiation. Derivative of this a z cube 3z square and into b as it is minus derivative of b, that is this one 5 by 2, so it is 5 by 2 z square r square 5 by 2 minus 1, so 3 by 2 multiplied by the a term here I written z cube. Here as it is z square, again we have taken the derivative of this is a constant, so therefore it is 2z divided by b square square of this entire term equal to 0. This part is a constant. So simplifying this, cancelling the common the power of z, and final solving this for a z, we get z is equal to 1.224. Okay, this is the depth at which the sigma z is maximum between 1 and 2. So in this table if I substitute 1.224, I get this value as maximum. You can see the maximum value which is calculated. So as this is 1 upon this, I get r by z 0.817. So in substituting the kb equations and sigma z, now sigma z is 88.0888, which is maximum between the 1 and 2 or entire table. Okay, so we got this is a stress distribution. You can see the r is a constant at a depth. This is the constant plane and z is a variable. So you can see how the stresses vary. First stress is very small, then increases, then again increases. Between 1 and 2 it was maximum at 1.224, which was the highest 0.088p, then it decreases. So this shows that the stress is not a linearly either increases or decreases. It has a trend, first increases and decreases. Now what is this point or what is this angle at which this is maximum? What is the angle between the constant r distance and z? So z is equal to 1.224 and constant r, the ratio we have taken. So if I take tan of that and find out this angle beta, I get 39.24. At this angle, this stress is maximum. So this is the stress distribution on a vertical plane. So here we completed the stress distribution on the horizontal plane, stress distribution on the vertical plane. Now we come to the third part, again a very important part, and this part is also very useful, particularly in our settlement calculation. So this is the third part. So isobar, basically this part is a combination of first two, horizontal and vertical distribution of sigma z. What is the meaning of a isobar? A curve or a contour connecting all the points below the ground level of equal vertical stress on a plane in all directions of equal radial distance. So imagine that there is a circle which is parallel to ground surface, suppose at a distance z. So at a particular radius, suppose the stress is constant, then what we'll do, I'll find out the radial distance r. So at all the point on this perimeter of circle that represent the stress sigma z, and which is constant at particular depth. Now if I change the depth, again I'll do, I'll keep the sigma z constant. Let us say this diagram. This is a plane I consider. Okay. I want at every point on this horizontal circular plane, the stress should be remain sigma z at a particular depth then I'll find out that radial distance in all the direction that plane on which sigma z is constant. Similarly, if I shift this circle on a smaller distance of z, again I'll keep the stress constant. Let us say in this example 20% of the load, whatever the load, 20% of that load, it means all the points the stress is constant. What is varying? Z is varying and R is varying. Any circle if I draw, I'll find out that R at which the radial distance is same. So there are the two concepts. One is the isobar, which is just like a 2D diagram. So any plane, the stress is a required one. Let us say 20% is the example of the load. Then the radial distance is say suppose r1. If I go less distance, then I get r2, r3, r4. So all the radius on which the stress is constant for a different depth, but the radial distance is changing. So this form is something like a point joining a equal stress. Unit of stress is also bar. That's why it's called as isobar. This is just like a 2D diagram. Now if I draw a same circle, if I rotate, suppose if I rotate about vertical axis and it rotate, it form a soil mass. Therefore this is called as a pressure bulb. So what we say in pressure bulb, soil mass bounded by an isobar is called a pressure bulb. It is a 3D formation. It's just like a 3D diagram. This is just like a 2D diagram. It is called as a bulb because in our conventional old type of electric bulb, you will find it has the bottom portion particularly, not in the neck, somehow similar. If I mark on any point on the that electric bulb and move the horizontal plane, the stress remains same, or any surface of that bulb, the stress remains same. What is changing? The radial distance is changing. Okay, so this is called as the isobar. This is very important part in our settlement. Okay, in settlement, what we consider that this is the mass which possibly involved in the settlement. Okay, which is correctly obtained from this pressure bulb. So this explanation is given here. Now how to calibrate this isobar or generate this? Again we'll go from the basic. Isobar can be plotted for a different intensity of load. It is always plotted with the intensity of load. For example, 100 kilonewton is the load applied P. Okay, and suppose I want a stress at only 10 kilonewton. I have to identify those vertical distance and radial distance, okay, on the point on a, and form a contour or a 3D diagram on which stress is of just a out of 100 it should form a 10 kilonewton per meter square. So if I take a intensity wise, I can consider it as a certain percentage of the load. For example, here 25% of the load. So I'm interested to draw a contour having a 25% of the load. Then we call it as a that isobar of a 25%, or the 3D diagram pressure bulb of 25%. So we can draw it for any required percent. Generally in a settlement analysis, 10% or 20% or 25% isobar or pressure bulbs are used for the calculation. So I need this isobar of a 25%. So how do I calibrate? How do I plot actually? So our Boussinesq equation with the function of load, that varying depth, and the varying R by Z. Here both are varying. Z is varying, R is also varying. So it is written in terms of influence factor where KB is 3 upon 25. Just keeping this variable P and Z square, remaining terms which function of R by Z is a KB. Now in this equation my required thing is that 25% of the P, so I substitute it here. Okay, so 0.25 P, so P get cancelled, here I substituted, and KB is equal to 0.25 Z square. So now isobar of this 0.25 P is plotted for a different depth Z by determining a corresponding radii, that is R1, R2, R3. So the details are given in a table. The sequence of this calculation is such that first you assume the depth Z, any Z1, determine the KB, substitute Z1 here, determine the KB, and then substitute in this equation that KB to get the sigma Z. So next you will see all these detailed calculations. Suppose the depth exactly is below the center. You can see the exactly below the center. It is suppose a 0.2. We know that what happened to the 0, which is earlier. It cannot be plotted directly. So taking a z depth greater than 0, any closed interval. Okay, let us say take 0.2. Okay, and then substituting in the equation of a KB, I got the value of a 0.01. Then substituting this KB in the equation of sigma Z, I get the value of sigma Z. Sorry. Substituting 0.2, first we got the KB, okay, and we don't require it because sigma Z is no. I'll substitute now in the equation of KB. Okay, I got the KB value. Substitute here is okay. Then no need to substitute here. It is develop here, and from this find out R by Z. Okay, so from this we got a R by Z as 1.92, and just multiplying to 0.2 Z value we get 0.384. So if I take any closed interval like this 0.2, 0.4, 0.6, 0.8, 1, 2, find out the KB values, R by Z and R values. Now what you found that R value, that is the radial distance, okay, this is a horizontal surface. Suppose I draw a horizontal circle, okay, having a radius of 0.384, everywhere the stress is a 25% of P, then that diagram we call it as a pressure bulb. In a 2D you can see at this radius distance first the stress at a distance of 0.38, both the point shows that it is 25% of the stress. So this radius, it means this horizontal circle goes on first increasing 0.25, 0.58, increasing and then decreases. It is increase 0.58, 0.59, then it decreases 0. It means you can see here the radius increasing, then decreases. Somewhere it is crossing to the R is 0, but we don't know that depth. If I try to plot a depth, a point for 1.4 after 1.4, you don't get these values of R. It means that the pressure valve or isobar has already crosses the 0. So how to find out this value? Here we got it at 1.38. So in our basic equation of the K, the stress and kb is equal to, if I substitute this kb here and then substitute r by z is 0, because radius is 0. When it crosses, the radius is 0. So if I substitute r by z is 0, and this kb value obtained from earlier equation 0.25 z square, again I am showing here. As this is 0, simply you get 3 upon 25 0.25 z square, find out z 1.38. So at 1.38, again you substitute in the kb equation, you get 0.47. R by z is, r is 0, that's why r by z is 0, the radius is 0. So isobar is crossing at 1.38 distance vertical. So this is how a isobar or pressure bulb is calibrated or plotted. Similar one we can plot it for a different intensity. Now what is the specialty here? If I increase the intensity, this is for 25%, if I go for 50%, as we know the stress is towards the or close to the surface is very high. As we go away, the stress decreases. So this is the pressure bulb of 25%. If I draw a pressure bulb of 50%, it will go up because stress increases. If it's 75%, again small isobar, 90% very small isobar. If I go far away like a 10% pressure bulb, it will move downward and outward. You can plot it even for 1% also. So it will further extend. That means how much soil mass is involved or it is influenced under the stress, we can decide by drawing this pressure bulb. So let us take one simple example. Here I have taken the two loads, 100 kilonewton and 200 kilonewton. Suppose they are a distance away 5 meter, but these two loads are in a x direction, parallel to x direction, and required is that a point is given n which has a x distance 2, y distance 3 and z distance 5. Here you have to find out vertical stress sigma z. We can also find out tau r z, shear stress. So this is the problem given. What we do, again the concept here, the principle of superposition is used. So let us consider only the first load. Assume that there is no second load, so first load is there. Look at the point n, is a distance x2, y3, z5. Okay, so from this x and y you can find out first r, that is 2 square 3 square, you get the r is 3.6. Now write down equation, Boussinesq equation, substitute this value of r by z, z required is 5 meter, r is 3.6, load, first load 100 kg, we get 0.672. Now this distance 2 is given from the first load, that's why it is given from the left, it is mentioned, that's why this distance is 2. Therefore when we consider the second load, neglecting the first, the distance from the 200 kilonewton is the remaining 5 minus 2, 3 meter. So that's why the point n has a coordinate 3. Y is remains same because loads are parallel to the x direction, and z is also constant, that is 5 meter. So repeating the same procedure, first you find out r. Now here 3 and 3, so substituting you get r is 4.24, and finding out the sigma z for a 200 kilonewton as a 0.986. By principle of superposition you can add these two, so you get a total stress a 1.658, and let us write the unit because it is kilonewton and meter square. Let us say kPa, kilonewton per meter. We'll take a second example here. uh, Here we'll try to plot a isobar for 100 kilopascal intensity of, okay. So the isobar I required is sigma z is equal to 10 kilopascal when the load applied is 100 kilonewton at a ground level. So when point load is applied, okay, of 100 kilonewton, so P is 100 kilonewton, sigma z I required 10, so percentage of intensity is 0.1, that is 10 by 100, okay. Intensity is 0.1%, stress I required of the P, so I can write sigma z is equal to 0.1 P. Similar calculations we are following. Instead of 0.25, now it is 0.1. Then we are written sigma z, P by z square influence factor, where Kb is a function of R by Z. Now here we substitute 0.1 P in this equation, so Kb is 0.1 Z square. Now before we go for this interval, okay, first we need to find out where this isobar it crosses the vertical axis. So where it crosses the vertical axis, it means the R value is 0, as we have seen in earlier the figure here. So first we'll find out this Z, like here in this case 1.38, then it will be easy to select the interval. So substituting that in the equation of that Kb, of this Kb, substitute 0.1 Z square is equal to this, which is the function of R by Z, and now here R is 0. We have to find out that Z, therefore we are keeping R is 0, and simplify this, you get 2.185. At 2.185 meter Z, R is 0, the isobar is crossing the vertical axis. So I can select any particular interval. I can take 0.2, 0.25, 0.1, any interval. Here I selected 0.3, interval of 0.3, 0.6, 9, 1.2, 1.5, 1.8, 2.1, and the last I am putting here 2.185, where I get the radius 0. And do the similar calculation as we discussed earlier. So every time when you have a Z, substitute the Z here, find out Kb, okay. From this equation of Kb, find out R by Z and find the R. So you get all the radius. So at all these radius with this depth, the sigma Z value is 25%, here 10% of the load. Okay, so you can draw a figure. I have not drawn the similar figure, you draw it as we have discussed in the earlier one, this way. This is all about today's lecture, and now I expect you will try these two problems to solve. This problem already we consider the horizontal distribution. Okay, now for this load, what will be the vertical distribution? There are two loads, distance 5 meter, and my R is at 2 meter from the 200 kilonewton. On this vertical stress, draw the pressure distribution. Follow the exactly similar concept of stress on a horizontal distribution is the first problem. Second problem is two loads are given 1.5 meter away. Here you have to draw the isobar. You cannot draw a combined isobar. Here you are drawing a two isobar, and let us check whether they are overlapping each other or separate. It is assumed that there is one footing, second footing. Because of that, two pressure bulbs are generating. Whether these pressure bulbs interacting each other or they are totally away. So solve this and send it on the same email. This time you write lecture number 2 and 3. Okay. In case of any queries, you can ask me the question through my email or my WhatsApp number. So now, after this, this is the a basic Boussinesq theory. Boussinesq theory is given for a point load, and we are seeing the horizontal distribution, vertical distribution, and combination of that. That is isobar or a pressure bulb. Now we'll go in the next lecture for a practical footings. If my footing is a line load, like a retaining wall, infinite length, or my compound wall, finite length, what will be the stress distribution? Similarly, if my load is a circular, what will be stress distribution? If it is square or rectangle, what will be the stress distribution? And if it is the embankment load, what will be the sigma z? Okay, this we'll see in the next lecture. After that, we'll go for an important chart called as a Newmark's chart. Okay, so till then, try to solve it and send me as I given the details. Okay, next lecture I'll continue maybe in next week, or probably if I get time in 1 or 2 days. Till then, be safe, don't go outside, and do the work. There are a lot of work for you, for me also. Because explaining this through a online required a lot of preparations. Every time we do not write in systematically in this way, everything in our mind, so it takes a time. So in that, I'm consuming more time by sitting at home. Okay. So once again, good day, be safe.